Notice you have seen this before and this. We now come to the last section of the syllabus, physics of the atom. As you can see, we have 6 formulae to deal with. First, we will review the structure of the atom as you have learned it in your chemistry class and your physics class and your general science class in lower classes. We know that it contains a nucleus with protons and neutrons, and around it there are energy levels called shells. The first one is called a K shell, and this shell could take up to 2 electrons. Then outside of that, you have the L shell, and this could take up to 8 electrons. Then you have the M shell, and this one could take up to 18 electrons. Then the N shell, 32 electrons up to. O shell, 18 or 32 electrons depending on the situation. You also have the P shell, up to 8 or 18 electrons, again depending on the situation. And finally, you have the Q shell, which could take up to 8 electrons. So depending on how many electrons you have in the atom. When compared to the shells, the nucleus is much smaller than shown here. If this Q shell is represented by the actual drawing here, then that nucleus is just something about the size of a full stop. To emphasize that point, if you think of the Q shell at the edge of a large sports stadium, then the nucleus, this nucleus here, is about the size of a tennis ball in the center of the stadium, which means that the atom is mainly empty space. And one other thing before we go from this drawing that you see here does not correctly represent what the atom looks like, because you may think that there are circles around the nucleus. Actually, there are not. These shells that you see here are not really shells. They are not continuous. They are the possible locations of the electrons at these energy levels. And they look like spheres within spheres. So think of one hollow ball in another one, and in a bigger one. If you were to cut them all across, this is what you will see. Like if you cut an orange, so that it is not flat like a disc. What you see here would be like a semi-sphere, half of a sphere. So I hope we get a proper picture of what the atom looks like. Now, you already learned about the number of electrons. If you have 1 electron, in the case of hydrogen, you would have that 1 electron in the K shell, as the first shell. If you have 2 electrons, as in the case of helium, the 2 electrons will be located in the first shell, which is the K shell. But if you have 3, as in the case of lithium, the first shell would have 2, and the next shell will have 1, and so on. Now, this pattern follows until you reach potassium and calcium, and we will look at that closer in the next slide. So as we said, in the case of hydrogen, with 1 electron, that 1 electron will be in the K shell, which is here. If we come to helium, 2 electrons, the 2 electrons will also fit in the K shell, like that. But then we come to lithium, which has 3 electrons. 2 would fit as we see here, and this third one will fit over here. If we go to beryllium with 4 electrons, we will have those 2 there, and we will have 2 here in the L shell, the second shell, and so on. You go to fluorine, you get 2 and 7. 2 and 7, that would be 6 and 1, 7. And then you come to neon, 10 electrons, 2 and 8. So those 2 here, those 7 and this one, 8. But now notice that the second shell has been filled with 8 electrons. When we come to sodium with 11 electrons, you would have 2, 8, and 1 going over to this next shell, which is the M shell, and so on. You go to magnesium with 12, you get 2, 8, and 2 until you reach chlorine with 17, and you have 2, 8, and 7. So I'm going to draw in those 7 now. That would be 6, and that one would be 7. That's chlorine. Argon is 18, so we get 2, 8, 8. That's 8. Notice that the M shell, that is the third shell in argon, has 8 electrons. You would expect that potassium, that has 19 electrons, would have 2 in the first shell, so far so good, 8 in the second shell, so far so good. But since this shell could take up to 18, you would expect that this third M shell will have 9. But that is not the case. What happens is it does have the 8, and this one here goes over to the next shell, which is highly unusual. So we have an anomaly with potassium, and basically the same thing happens with calcium. With 20 electrons, you have 2 in the first shell, so far so good, 8 in the second shell, so far so good. But since the third shell can take 18 electrons, you would expect that this third shell should have, this third shell, this yellow one here, should have 10. But that is not the case. The third shell has only 8, not 10. Just like up here, the third shell has only 8, not 9. And then the fourth shell has 2 electrons. So that's the first shell, 2, the second shell, 8, the third shell so far is also only 8, even though it should be 18. And then we have the fourth shell, which is the N shell. We do have potassium with 1 electron there and calcium with 2. Now, as far as CXC is concerned, CSEC, you do need to know the electronic configuration of the first 20 elements, that is to say, up to calcium. Bear in mind that from 1 to 18, you have a pattern. 19 and 20, the pattern breaks down. As you can see, when we come to these transition elements here in red, you can see now the 8 becomes 9 and 10 and 11 and 13 and 13. But that's a 13 1 and a 13 2, a 14, a 15, a 16, an 18 1, and an 18 2. But the thing about it, once you reach here, Papa, you have reached 18. Remember this 18 here. And so on. Now, by the way, what is on this slide is just for your information. For CSEC exam, all you need to know is how the electrons are distributed up to 20 electrons, which would be calcium. And you don't even have to memorize how many electrons are in these 20 atoms or elements. That will be provided for you in the standard notation. So now we get to equation 1. A is equal to Z plus N. In that formula, A is the nuclear number, which in chemistry is referred to as a mass number. Z is the proton number, which again in chemistry is referred to as the atomic number. They are the same things. And N is the number of neutrons. So here is a standard notation. X represents the element. This number up here, A, is the nuclear number or the mass number. It's called nuclear number because it tells you the total number of things in the nucleus. That is to say, the total number of protons and neutrons. And this number down here, Z, is called a proton number because that is the number of protons in the nucleus. It so happens that that is also the number of electrons around the nucleus in a neutral atom. So Z is the number of electrons, which is the same as the number of protons in an unreacted, a neutral atom. It is also called the proton number in physics and the atomic number in chemistry. That's Z. A is the sum of protons and neutrons in the nucleus of the atom, and it is called a nucleon number because it's the total number of things in the nucleus, or you would hear it also called in chemistry as the mass number. N is the number of neutrons in the nucleus. So N is equal to A minus Z. So this is the nuclear number, total number of things in the nucleus. That's the number of protons. So if you subtract the number of protons from the total number of items in the nucleus, you will get the number of neutrons. Now, let's look at example 1. Carbon has a 14 up here and a 6 down here. Now, this is carbon 14, not carbon 12. Now, Z is the number of electrons, which is the same as the number of protons in an unreacted atom, and it is called the proton number as well as the atomic number, and in this case, that is 6. This 6 here. A is the sum of protons and neutrons in the nucleus, of course, and is therefore called a nuclear number or the mass number, and in this case, that is 14. So if in a nucleus has 14 protons and neutrons, and that same nucleus has 6 protons, then how many neutrons do we have? All we need to do is subtract the 6 from the 14. N is the number of neutrons in the nucleus, so you have 14 minus 6 and you get 8. One more thing, since we have 6 electrons, we need to know the electronic configuration. So the first shell would have 2 and the second shell would have 4. That's example 1. Example 2, sodium, 23 and 11. Z is the number of electrons, which is the same as the number of protons in an unreacted atom, and therefore it is called the proton number or the atomic number. So in the case of sodium, you have 11 protons in the nucleus. You also have 11 electrons orbiting that nucleus. That is 11. This is Z. A is the sum of protons and neutrons in the nucleus, 23. So if you have 23 protons and neutrons, and you have 11 protons all in the nucleus, then obviously if you subtract 11 from 23, you will get the number of neutrons. So n, which is the number of neutrons, is 23 minus 11, and you get 12. The electronic configuration for sodium, which has 11 electrons, is 2 in the first shell, 8 in the next shell, which will give you 10, and 1 in the third shell. Example 3, fluorine, 19 and 9. By now, you know that this Z is the number of protons in the nucleus as well as the number of electrons around the unreacted atom. So you have 9 protons in the nucleus and 9 electrons around it. That is Z. A is the sum of the protons and neutrons. It is called the nucleon number, meaning the total number of items in the nucleus. So it is the sum of the protons and neutrons. So you have 19 here. That's A. And of course, if you have 19 protons and neutrons and 9 protons, then the number of neutrons would be 19 minus 9, and that would give you 10. Let's look at the electronic configuration with 9 electrons, 2 in the first shell and 7 in the second shell. Example 4, sulfur, 32 and 16. So now you know 16 is the proton number, which is also the number of electrons around the nucleus. Z is the number of electrons, which is the same number of protons in an unreacted atom, called the proton number or the atomic number, and it is 16. This one up here, 32, A, is the sum of the protons and neutrons in the nucleus of an atom, and it is called the nuclear number. And in chemistry, you hear that as the mass number. In this case, it is 32. That is A. So, of course, if you subtract 16 protons from 32 protons and neutrons, then you are left with 16 neutrons. The electronic configuration, 16, will give you 2 in the first shell, 8 in the second shell, that will give you 10, and 6 in the third shell. Now we look at potassium. Be careful with this one. 19. Z is the number of electrons around the nucleus. It is also the number of protons in the nucleus. So it is called the proton number or the atomic number. And in this case, it is 19. A, which is this one up here, is the sum of the protons and neutrons in the nucleus of an atom, and therefore it is called a nucleon number, number of items in the nucleus. Or you may hear that referred to as the mass number as well. That is 39. Now, how do we get the number of neutrons? We subtract from 39, we subtract 19. So 39 minus 19, number of neutrons. Now be careful with this one and its electronic configuration. First shell has 2, second shell has 8, third shell does not have 9, even though that shell could take up to 18. Third shell has 8, and the fourth shell has 1. So it's 2, 8, 8, 1. And for calcium, which is 20 down here, it will be 2, 8, 8, 2. Example 6. If the nucleus of an atom contains 33 protons and 42 neutrons, what is the nucleon number? Well, if you know that that Z there is 33, and you know that this N here is 42, then what is A? Well, A is equal to Z plus N. So we know Z, we know N, we want to find A. A is equal to Z plus N, you just add them up and you get 75. So the nuclear number or the mass number of the element represented by that atom, whatever it is 75. Example 7, helium, 4 and 2. Now we know that helium would have 2 protons, would have 2 electrons configured in the first shell, and it would also have 2 neutrons. So you can easily draw that structure if you are asked to draw it. Fluorine with 19 and 9, it has 9 protons in the nucleus. It has 9 electrons around the nucleus, 2 in the first shell and 7 in the second shell, and it has 10 neutrons in the nucleus. Aluminium. Now notice I said aluminium and not aluminum. Aluminum is American. We are doing a British Heritage exam, so I would say aluminium. Aluminium, 27 and 13. 13 protons, 13 electrons, 2 in the first shell, 8 in the second, and 3 in the third, and you have 14 neutrons. Subtract 13 from 27, you get 14. So I think you should be able to manage this first formula very well. Let's move on. If you find this video useful, please like, share, and subscribe to this channel. It wouldn't cost you anything, and it will mean a lot to me. I think everybody looking at this video knows what this picture here is. It's the periodic table. You have the elements properly organized in rows and columns. The columns are called groups and the rows are called periods. And there is a system that is used to organize all the elements in that table, which we will not get into right now. Now, this is that same table, except now the names are shown, like cadmium and arsenic and titanium and magnesium and so on. As you use these, you will remember those that you need for this class. So we come to the second formula, which deals with alpha decay. A, which is that nuclear number, decreases by 4, and Z, which is the proton number, decreases by 2 when you have alpha decay. Sometimes the energy required to keep the number of protons and neutrons in the nucleus is not enough. The energy is not sufficient because the ratio of the neutrons to the protons is too great. So a spontaneous reaction or shakeup occurs in the nucleus, spitting out particles and energy, leaving that ratio of neutrons to protons acceptable for the available energy in the nucleus, resulting in a different atom or element. And that action there is called radioactive decay. The 2 types of particles that may be given off are alpha particles and beta particles, and the energy is in the form of gamma rays. So this formula here, formula 2, deals with alpha particle decay. The original atom or element is called the mother element, and the new atom or element is called the daughter element. The daughter element will have nuclear number 4 less than the mother element and a proton number 2 less than the mother element. This is what always happens during alpha decay. So let's look at a few examples. If X is the mother element, and we have A here as the nuclear number and Z as the proton number, we get out a helium ion, which is He24, plus Y. Now notice that this number on the top left of Y decreases by 4. That's because of this 4 here. And so the nuclear number of Y is 4 less than X. And the proton number of Y is 2 less than X. That is because of this 2 here. So let's look at a few examples. So as I said, that is the mother element, that is the daughter element, and this is helium, the alpha particle. Example 1, if you have uranium 23392, that will give you a daughter particle of thorium plus helium. Well, we know helium is 4, 2. Now, in the case of thorium here, what do we have at this point and here? Well, we said that this will decrease by 4, that 4 there. So this number up here will be 229. And this one down here, the proton number will decrease by 2, by this 2 here. So now we have 90 here. So this number decreases by 4, and this one decreases by 2 in the daughter element when compared with the mother element. Let's take another example, example 2. We take thorium. This is not that same thorium up there. That one is 229. This one is 232. And we get radium with helium. Remember, this is alpha decay, which is always helium, which is 4, 2. By now, you know that the number up here for radium will be 4 less than that we had over there. So we get 228. That's the nuclear number. And the proton number for radium will be 2 less than that. So we get 88. Let's look at example 3. Gadolinium, which is 149 and 64. And that would give us samarium and, of course, helium. So when we look at this samarium in comparison to gadolinium, you notice that this here will be 4 less. So we get 145. And this proton number will be 2 less, that 2 there. And so we get 62 here. Please note that if you add this and that, you will get that one up there. And the same thing applies to this 62 and 2. If you were to add those 2, you will get back 64. Example 4, platinum, 78, 175. That would give us osmium plus, of course, helium, because we are dealing with alpha decay. Alpha decay is always helium. So what do we have here for this osmium? What is its nuclear number and what is its proton number? If you take 4 away from that 175, you will get 171. And if you take 2 away from that 78, you will get 76. Example 5, Neptunium 93 to 37 will give us protactinium and of course helium. By now you know that the number here, the nuclear number for protactinium would be 4 less than this 237, so it would be 233, and the proton number will be 2 less than 93, and so we get 91. So for alpha decay, the nuclear number decreases by 4 from the mother to the daughter. The proton number decreases by 2, and the particle that is ejected is actually a helium ion, He 2+. That is for alpha decay. The total nucleon and proton numbers are the same on both sides of the equation, or the arrow. So that 233 plus this 4 must be equal to that, and this 91 plus that 2 must be equal to that. And that is one of the nuclear reactions we need to know about. There are two. First one is alpha decay. Now we come to beta decay. Now in this formula deals with beta decay. The original atom or element is called the mother, as we already know, and the new atom or element is called the daughter. When compared with the mother element, the nuclear number of the daughter element remains the same, while the proton number increases by 1. This is totally different from what we were doing for alpha decay. So if the element is X, and this is the nuclear number, and this is the proton number, notice that the daughter element Y, the nuclear number stays the same, whereas the proton number increases by 1. But what do we get out? Instead of helium, we get high energy electron, written that way. 0 up here and -1 down here. So this is the second of the nuclear reactions that we have to do. As we said, that is the mother element, this is the daughter element, and this is the beta particle decay, which is high energy electrons. So let's look at some examples. Example 1, if we take helium 2,6, now this is not your regular helium, it's an isotope of helium. From that mother element, we get lithium, and of course, we get an electron. Right now, you may be wondering, since all of this is taking place in the nucleus, where does that electron come from? And to make matters a little more confusing, yes, this remains as 6, but this 2 here will become 3 over here. And you are tempted to say, what is going on? So let's see what is going on. If you didn't know this before, it may come as a surprise to learn that the neutron, or a neutron, is actually made up of a proton and an electron. A neutron that is in the nucleus, that we said only contain neutrons and protons, well, each of those neutrons is actually made up of a proton and an electron. So this is what happens. One neutron spits out its electron, which is this beta particle, and becomes a proton. One more proton means that the proton number increases by 1. That is where you get this plus 1 from. Proton number increases by 1. But since you have one less neutron and one more proton, then the total number of items in the nucleus A remains the same. And so you have this 6 remaining as 6. So the proton number increases by 1, and the nuclear number, which is the mass number, stays the same. Now, this was example 1 for helium. Let's look at another example. Sodium, 11, 24, not the typical sodium 23. So sodium 24, you get magnesium from that, plus, of course, our electron, our beta particle. Now, this here stays the same, which is 24, doesn't change. But this 11 increases by 1 over here, because remember, you get an extra proton in the nucleus, and that becomes 12. And this is what happens for beta decay. Example 3, let's deal with gold, 97, 201. That is the mother element. And that gives us mercury plus the electron, our beta particle. Well, this mercury here has the same nuclear number as gold, which would be 201. It doesn't change. But this 97 over here becomes 98, because we now have an additional proton from the one neutron that broke apart to give this electron. So this becomes 98. So the nuclear number is unchanged here, unchanged, 201, 201. The proton number increases by 1. 97 becomes 98, and so on. Example 4, let's take iron, 26 and 52, which gives us cobalt, and of course, an electron, which is a beta particle. This cobalt here, if that is 52, then this here remains as 52. This 26 down here becomes 27. That's for cobalt. Incidentally, you may or may not know that iron, cobalt, and nickel are the only 3 magnetic materials we know of on Earth. And I'm wondering, why is that so? Copper, which is right to the side here, and zinc, they are not magnetic. Manganese and chromium on the other side, 24, 25, they are not magnetic. The only 3 magnetic materials we know of on Earth are iron, cobalt, and nickel. If you have any other material mixed with those, one or more of those will also be magnetic. So if you take a bunch of keys and you put a magnet next to it, you may find some of them may be attracted to the magnet. Those contain one or more of iron, cobalt, or nickel. But then you have other keys that are metal. They will not be attracted to the magnet. Then those do not contain any iron, cobalt, nor nickel. That is just an aside. Let's come back to example here. Beta particle decay. Example 5, potassium, 19 and 42, which gives us calcium. Now remember the potassium and calcium business we were talking about, and their anomaly as it relates to the third shell and the fourth shell electrons. Okay, of course we get our electrons. Calcium 42 here, 42 there, no surprise. It is beta decay, but this 19 over here must become 20. Again, the same thing applies. If you add the nucleon numbers over here, if you could call this 0 here a nucleon number, you must get the same number on the left-hand side. And then if you add these numbers below here, 20 plus a negative 1, you will get back 19 on that side. So the particle that is ejected is an electron. It is a high energy electron. The sum of the nucleon and proton numbers are the same on both sides of the arrow or the equation. For gamma radiation, A and Z remain unchanged. The emission of gamma rays, now notice these are not particles. Alpha particles are particles. They are helium ions. Beta particles are particles. They are high energy electrons. But gamma radiation is exactly that, radiation. They are not particles. And their emission, you have no change in the number of protons and neutrons in the nucleus. Rather, this causes the nucleus to go from a high energy imbalance to a lower energy balance. So the nucleus becomes less unstable. So actually it becomes more stable, but we can say less unstable. Gamma radiation occurs when other particles, example alpha and beta, are emitted. Now, summary up to this point, we will look at one example to see if we have learned the concept of alpha and beta decay. Assume that there is a radioactive element A and it has nucleon number 205 and proton number 97. It undergoes an alpha decay to form B, then B undergoes a beta decay to form C, and then C undergoes another alpha decay to form D. How many protons and neutrons does D have? Let's begin with A, 205, 97. We have an alpha decay, so we get helium, and we get B. So now B would be 201 and 95. Remember, we subtract 4 from that to get this, and so on. Now B becomes C, but C decays by a beta decay. So we get an electron plus C. In this case, this 201 remains unchanged, so we have 201. This 95 would be increased by 1, so we get 96. C, of course, undergoes another alpha decay to form D. So now we have alpha decay, helium, and we have D. Well, this here will decrease by 4 from what it was, so 201 becomes 197, and this down here will decrease by 2 from 96, and we get 94. And the question is asking, how many protons and neutrons does D have? Well, as it stands here, we know that it has 94 protons. Number of protons is 94. This is the proton number. Now, how many neutrons does it have? You subtract 94 from 197, and you get 103 neutrons. Any gamma emission will not affect these numbers. And this brings us to the end of this video, Physics 20.